The next segment that we're going to do in Module 2 is the atomic level of organization, and here we're actually going to look at those atoms that we talked about earlier. So we have objectives 8 through 10, which have to do with protons, neutrons, and electrons. These are the subatomic particles that make up atoms. So electrons and protons and neutrons are the largest of the subatomic particles because these were the first discovered in the latter part of the 19th century, the early part of the 20th century. We call these elementary particles. The protons and the neutrons form the nucleus of an atom. The electrons surround the nucleus in a cloud, as we'll see a little bit later on. Electrons have a negative charge, and they're very small particles with very little mass or weight to them. So they're negatively charged and small. They give the atom its chemical properties. So it's the trading and the sharing of electrons that give the atom's ability to form bonds and have these chemical properties we'll talk about later on. We have specific objectives for these in looking at valence and charge. And these are on the outside, and that allows them to interact with other atoms. So these electrons surround the outside of the atom. They rotate around the periphery. They orbit around the periphery of the atom in a probability cloud, as we'll see in just a minute. And so they surround the nucleus of the atom, and because they're on the outside, they're able to interact with other atoms. The protons and the neutrons, on the other hand, are found in the nucleus, and that means that they don't interact with other atoms. The protons are positively charged, and they're large particles that form part of the nucleus. The neutrons are like protons, but they have no charge. So they have a similar mass, but they have no charge, and they are part of the nucleus. So the nucleus is made up of protons and neutrons. Surrounding the nucleus of the atom are the electrons that are there in a probability cloud. That's the real model of an atom, is a probability cloud, or what's called the electron cloud model. This has to do with things that were discovered, you may have heard of, discovered by Werner Heisenberg, called the Heisenberg uncertainty principle, that we can either know the position of an electron with certainty, or we can know its mass with certainty, but we can't know both. And that turns out to be true for all the elementary particles, that we can know their position or their mass, but not both at the same time. This is called the Heisenberg uncertainty principle. One thing that comes out of that is the electron cloud model, that we have a general idea of a probability of where electrons are. We can say with some certainty there's a 80% probability that it will be in this location, or a 20% probability that it will be in that location, but that's as far as we can go with that. This is what made Einstein famously say, well, God doesn't play dice, because he refused to believe that this was the case. But it turned out even as smart a guy as Einstein was wrong about this one thing. And the electron cloud model is something we're not going to use a lot in this course, but for other courses and for really having a deep understanding of how the way the world works, we're going to need to understand the electron cloud model. But for our purposes in this course, we're not going to use the more correct electron cloud model. We're going to use the less correct model that's shown on the right here, called the electron shell model. The electron shell model is the older model. We also call this the planetary model of the atom, because the electrons then occupy specific shells. These correspond to specific energy states, higher and lower energy states, like planets orbiting the sun. And so in this analogy, the nucleus is the sun, and the electrons are the planets that orbit around this. We find the electron shell model really useful for the chemical properties that we're going to talk about, the chemical properties of life that we're going to talk about in this course, and so that's mainly what we're going to focus on. But we always want to remember that the electron cloud model is the more correct one. We're just using the electron shell model for our convenience. So electrons, as I said earlier, are very small, they're very light. Their mass is only about 1/2000th that of a proton or a neutron. So as we'll see in just a minute, they don't contribute very much to molecular mass. So if we define the mass of a hydrogen atom as 1 Dalton, then the mass of an electron is 1/2000th of that. If we take 1 and divide it by 2,000, then we'll get 0.0005 Daltons, which is 5 times 10 to the negative 4th Daltons. That turns out to be about 9 times 10 to the minus 28th grams, or 1 divided by 9 followed by 28 zeros. As you can imagine, that's a very, very small number. So there's a lot of atoms that make up 1 gram of material. 1 Dalton is an atomic mass unit. So we'll see this used interchangeably, either as an atomic mass unit or a Dalton or a capital D little a. And those are what are called atomic mass units. So this is the mass of a hydrogen atom. And it's not just any old hydrogen atom, but it's a hydrogen atom, as we'll see later, that's made up of 1 proton and 1 electron, is 1 atomic mass unit, or 1 Dalton. As atoms get bigger, they're going to be more massive. They're going to have more weight once we have gravity on them. So if they're more massive, then we're going to increase their atomic mass. And we'll see that as a number in the periodic table. As I said earlier, we're going to use the planetary model in this course. In reality, we need to remember that it's a cloud of probability. Even people that are pretty smart, like Albert Einstein, Richard Feynman, struggled with this concept. So Richard Feynman said, and that's the quote you see under here, that nobody understands quantum mechanics. So this idea that protons and electrons and other subatomic particles exist only as a probability cloud is what we mean by quantum mechanics. And Richard Feynman, who won the Nobel Prize in Physics, and so he should know what's going on here, he says he doesn't understand it, that nobody understands quantum mechanics. And as you'll see if you get into this in other science courses, you get into this more deeply, that quantum mechanics produces some really weird behaviors that are fundamental for our understanding of the universe, but not fundamental for our understanding of the human body, which is what we're in this course for. So in this course, we're just going to use the planetary model because it'll be much easier for Richard Feynman and Albert Einstein and Werner Heisenberg and me and you to understand. The next subatomic particle we're going to look at is the proton. Protons and neutrons form the nucleus of an atom. The electrons are surrounding the nucleus. The protons have a positive charge. That's where the pro comes from. They're positive. They're in favor of something. So positive protons. Positively charged large particles, they have a mass of 1.007 Daltons, or 1.007 atomic mass units, and they're part of the nucleus of the atom. The neutrons are the other part of the nucleus. Neutrons are large. They have almost the same mass as protons. It's 1.009, so they only differ in mass down in the 3rd decimal place. Basically, protons and neutrons have a mass of 1 Dalton, 1 atomic mass unit. And these are part of the nucleus as well, but they don't have a charge, as I said. Protons, represented as the red balls here, have a charge, and neutrons, represented as the blue spheres, have no charge, and they have about the same mass.